Hey guys, so today what we're going to do is just kind of have a brief introduction to Chapter 10. We'll introduce some of the underlying concepts as well as introduce the three basic formulas that we'll use for this chapter. But we really aren't going to go into much depth in this video. We're just going to kind of broadly introduce things, and then we'll go back in the coming videos and look at the situations where these formulas and situations apply. So today's purpose is not necessarily to enable you to solve calculations or answer questions. It's just to give you kind of a broad introduction to the topic. So the overall topic of Chapter 10 involves the heating and cooling of substances, as well as the associated energy and phase change that occurs with that. So if we go ahead and jump right in, one of the big things we need to look at to start off with, we have a new symbol, capital Q. Okay, so in this class, we'll use capital Q to represent the energy associated with heat. Okay, so it can have units of joules, kilojoules, or calorie. And we'll talk more about the C's in a minute. Just kind of be aware those are some different units for the energy there. So heat energy, or Q, as we'll refer to it, is a measure of the total amount of energy in a system. Okay, so anytime I'm describing the heat energy or the Q, it's a measure of the total amount of energy present. The other idea you likely already have about heat energy probably is temperature. Okay, so you have some background knowledge of temperature. So now the big difference here is, you be sure to write this down, temperature is a measure of the average energy of a system. Okay, so Q measures total heat energy, and temperature is a measure of the average energy. Okay, so we'll come back to that. What I want to do now, after you have those two terms straight, is really introduce three different calculations and formulas that we'll do. Okay, so the first calculation formula that we'll look at, we have a couple of new symbols for it. The first is HF, and you'll typically see it written H subscript F. So HF we'll call the heat of fusion. Okay, so the heat of fusion, and I'll tell you what it's equal to first. Well, let's talk about what it is first. So heat of fusion is typed out is the amount of energy needed for 1 gram or 1 mole, and we'll talk about the distinction there for 1 gram versus 1 mole, to undergo the phase change of melting or freezing. Okay, so if you think about melting and freezing, try to associate that with fusion. So whether the energy is absorbed or released kind of depends on whether we're melting or freezing, but either way you have the same value. Okay, so the same energy that is required to melt an amount of a substance is what is released, or not absorbed rather, when you have the opposite process of freezing going on there. So the reason we say 1 gram or 1 mole is because we can have a couple of different units for HF, heat of fusion. We can have it expressed in joules per gram or joules per mole. And that's what tells us which definition we use. It's either the amount of energy needed to melt 1 gram or 1 mole of that substance. Okay, so the way we define that is the amount of energy required divided by the amount. AMT means amount. So that could be really grams or moles there. But really we'll never calculate HF. That'll be given to us. Those are known values. So there are tables throughout the notes. So for water, the HF value is 334 joules per gram. For gold, it is 64.5 joules per gram. So those are known values. So don't worry so much about calculating HF. What you need to know is how to apply HF. So we have a formula, Q equals amount times HF. You'll also see it written Q equals HF times M, where M stands for mass. So we can use this to calculate the amount of energy required to melt a certain mass of a substance. Okay, so I could use this to figure out how much energy is required to melt 15 grams of ice, and to do that I would need the constant from the table in the notes. Okay? So the big takeaway here for this are these two lines. Use HF for the process of freezing or melting, and you have Q equals amount times HF. Okay. You could also use Q equals HF times number of moles in this formula, but for that you would have to have a constant in terms of moles, and all our constants in the notes for this are given in terms of grams. Okay. So then we have another very similar symbol. HV is the heat of vaporization. So that is the amount of energy needed for 1 gram or 1 mole, the same situation depending on the units, to undergo the phase change of vaporization or condensation. Okay, so the exact same concept, but different phase change here. So I could rewrite this as Q equals HVM. So I could use this to calculate the amount of energy required to vaporize or evaporate a certain mass of water or some other substance. Okay, so the formulas are very similar and they do the same thing. You just have to decide based on your phase change if you use the HF constant or the HV constant, and that depends on what phase change you're performing. And keep in mind, these constants are specific to a certain substance. Okay, so every substance has a special HF value, every substance has a special HV value. And even for the same substance, these two values are different. Okay, so keep that in mind. So then, those are really the two formulas that we'll use for phase changes. So anytime we have a phase change, you want to calculate how much energy is needed for that phase change. Those are the two formulas that we use. So now we need to look at a way to calculate the energy required to heat a substance when a phase change is not happening. Okay. So if we're just heating water from 5 degrees Celsius to 10 degrees Celsius, there is no phase change. However, I do have some energy that is absorbed for that. So the first thing we need to look at is we have a new symbol, C. So C is the specific heat capacity. So notice we talked about C up here. This is the unit C. Okay, so the unit C stands for calorie. The symbol C stands for specific heat capacity. Okay, so if you have C in a formula such as this, it stands for specific heat. But if you see 17C, you see C after a number, that refers to calories, the unit for energy. Okay, so specific heat capacity is defined as the amount of energy needed to raise 1 gram, and we'll leave off the 1 mole. Is typically expressed in grams, 1 gram of a substance by 1 degree Celsius or Kelvin. And as before, this is dictated by the units here. So if I have this unit, for example, for C, this is joules per gram degree Celsius. So this is the number of joules required to heat 1 gram 1 degree Celsius. Okay? And you could also have in other units, kilojoules per mole degree Celsius. So if the units on C were this, that would tell you that is the number of kilojoules required to raise 1 mole of a substance by 1 degree Celsius. Okay, so where we use this is we have a new formula. Q equals M times C times delta T. So delta is a Greek letter that means change in. Okay. So how much does the temperature change? Does the temperature go up by 5? Does it go down by 5? We really have to subtract there. So we don't plug in individual temperatures, we plug in the temperature change that we have. So if I have a question where I ask you how much energy is needed to heat 2 grams of water by 10 degrees Celsius, so from 10 to 20 for example, the delta T is 10 because we changed 10 degrees. And here the M typically stands for mass, but again that depends on the units for C. So C again is a constant that is specific to the substance that we have. Okay, so here if we go to this table for water, I have a C subscript L. So that is the C value for liquid water. It's 4.18 joules per gram degree Celsius. So it takes 4.18 joules to raise 1 gram of liquid water 1 degree Celsius. Then I also have a different C value for, that's G, gas water. Okay, so water vapor. So it takes 2.02 joules to raise 1 gram of water vapor 1 degree Celsius. Then there is a C value for solid water. So ice. It takes 2.06 joules to heat 1 gram of ice 1 degree Celsius. And there are also different C values for the other solids we have, gold, silver, and copper here. So this is a very useful table that we will use quite a bit. And if you're ever given a problem and you aren't sure what state of matter it should be in, whether it's a solid, liquid, or a gas, you can look at the boiling points and melting points given in this table to decide if it's a solid, liquid, or a gas. So if water's below 0, it's a solid. Between 0 and 100, it is a liquid, and above 100, it's a gas there. So we'll come back and look at that last formula later, MC delta T equals MC delta T. But for now, let's just kind of summarize the three formulas that we've talked about, and I'll write these down here at the bottom. So first, we have Q equals HFM. So I would annotate this on your paper what it means. So Q is heat energy, HF is heat diffusion, it's a constant, and M is mass. And I use this for a solid to liquid phase change. Okay? And this is only for a phase change. So write this down, this is important. There is no temperature change during a phase change. I repeat, there is no temperature change during a phase change. So notice there is no delta T in here. Okay? So as the water melts, temperature does not change. Or water. We use water as the common example, but really you could use any compound here. The same situation works. So then I have Q equals HVM. So that is for the liquid to gas phase change. So again, Q is heat energy, HV is our constant heat of vaporization, and M is our mass in grams. Again, notice there is no delta T here. So what we have to do is, if there is a delta T after the phase change, use other formulas, but this only accounts for the phase change where there is no temperature change. Then the last one, we have Q equals MC delta T. So heat energy equals mass times specific heat times change in temperature. So this is used for temperature change. And you might want to make a note, temperature change with no phase change. This formula cannot be used for a phase change because C values are specific to a certain state of matter. Okay, so we have to use this only within a certain state of matter. So now we have three different equations that allow us to calculate the energy required to heat a substance, to melt a substance, and then vaporize a substance. Okay? So in the coming videos, we'll learn how to apply those to a variety of situations. So before we end this video, one thing to look at, you can read this little section on your own. And it's not super important, it's kind of an FYI thing. We don't use the unit calorie very often in chemistry. We typically use the unit of joule for energy. But this is where the calories on your food label come from. They are a unit of energy. And if you've ever been to a country other than America, you've probably seen that some countries, their calorie content on their food is significantly higher than what you're used to seeing. That's because there's two different versions of the unit calorie. There's the capital calorie and lowercase calorie. So one capital calorie equals 1,000 lowercase calories. I know it's somewhat confusing. So just keep aware, if the ones we use in chemistry are different from the ones printed on food labels, however, they are related by a factor of 1,000. Okay, so we have the conversion factors here. And more importantly, there's a conversion factor between joules and little c there, lowercase calories. So don't be so worried about that. We really won't ever use the unit of calorie for energy in this class. Just be aware, calorie is a unit for energy that can be related to joules. Okay? So the next two videos that you'll have will kind of explain the couple of phase diagrams here and a vapor pressure chart, and then you can answer those questions. Then we'll come back in the next video and look at the heating diagrams and how to apply these situations.